the sum of digits function we wrote in the last lesson seems to be very natural, right? And in fact, it seems so natural that it's hard to imagine how one could write this function in a different way. But this intuition is wrong, completely wrong. In fact, there's a second approach to write this function, a quite different approach that leads to another and even better definition. So to introduce this approach, let's start with a simpler function than sum of digits. Let's start with a factorial function. This will let us focus on the key insight. After we treat the case of factorial function, we'll come back to sum of digits. So the factorial function, first we will give its mathematical definition. So 0 factorial is equal to 1 and n factorial is equal to n times n minus 1 factorial when n is bigger than 0. This mathematical definition is called the specification of the factorial function. It's purely mathematics. There's nothing in there that is connected to programming as such. It's just a mathematical definition. Now we can take this mathematical definition and follow it to give our first implementation of factorial. So we declare a function fact1, argument is n, and now we follow the definition. If n is equal to 0, then we return 1. Otherwise, we return n times the factorial of n minus 1. Okay, this follows quite closely the mathematical definition. Let me feed it to the system. We have here an error. It's a very common error. Do you see it? In fact, I didn't call the recursive function fact1. I should have called it fact1. Let me redefine the function now and browse fact1 of 10. Let me try factorial 10. This gives me 3,628,800, which is factorial 10. Okay? This is the first implementation, which is actually very similar to the sum of digits implementation. Now let's go to the other one. The other one uses an idea which I like to call the principle of communicating vases. Let me bring in a diagram and let me explain how this approach works. So the way it works is we start by inventing a formula that splits the work we have to do into two parts. So here I have the formula n factorial is equal to I factorial times a. N is the number we want to calculate. I and a are new variables that I introduce. So the I factorial is one part and the a is another part. So we will start with I is equal to n and a is equal to 1. Notice the formula then is true. We have n factorial equal n factorial times 1. And the idea now is to decrease I and increase a in a single step, but in such a way that the formula remains true. And if we can keep doing that until I is 0, then when I is 0, a will be the result. Okay, so here's an example when n is equal to 4. We start with 4 factorial equal 4 factorial times 1. I is equal to 4 and a is equal to 1. We now decrease I from 4 to 3. So we've divided it by 4. So we have to bring in a 4, otherwise the formula is no longer true. So we multiply the a by 4. So that gives us 3 factorial times 4. Now we continue. The 3 factorial becomes 2 factorial. We've actually divided it by 3. So we have to multiply the a by 3. 4 times 3 is 12. And we continue. 12 times 2 is 24. 24 times 1 is 24. And the result is 24. So that's the idea. Now we have to find a general formula that works in all cases. So let me see how we can find that. So the principle of communicating vases, we start with I factorial times a. Now we will decrease I, and then we'll see how a has to increase. So I becomes I minus 1 factorial, but we've actually divided it by I now. So we have to bring in an I to keep the formula true, and we still have the multiplication by a. So we can say this is I minus 1 factorial times I times a. Okay? Now with this formula, we can actually make a second definition. Okay, let me get the diagram out of the way. Let me now do a second definition. Second implementation of factorial. So declare function fact2. the I and the A that we've introduced become arguments to this function. Remember the end condition: when I is equal to 0, then the result is A. Otherwise, we have to do the decrease and increasing step. So I minus 1 and I times A. You notice that this corresponds exactly to the formula we came up with a little bit higher. So this is our new function, fact2. So let me now feed this to the system. Browse. We will call fact2. Let's do the same factorial. 10 factorial, so 10 and 1. So let me call this. And this gives us the same result, 3,628,800. So now we have two definitions. Okay? This original one, which followed the mathematical specification, and then this rather different one, which does the calculation rather differently, but still comes up with the same result. So it should be clear also why we call this approach for the second implementation the principle of communicating vases, with the one argument decreasing and the other one increasing. Another name for this approach is called invariant programming, because the formula n factorial equal I factorial times A is always true, so it's an invariant. So this is a kind of motor. We can push the I and the A in the direction we want. As long as the formula stays true, the program will do the calculation that we want.